optode co-registration yields better channel localizations in fNIRS and improves spatial reconstruction in DOT. This is a quick tutorial on how to perform a photogrammetry scan using the handheld 1-star 3D scanner from the company Shining 3D. I also quickly show on one example how the recording can be replaced by iOS or Android smartphones and free apps. The output of this pipeline is an OBJ file which can be directly loaded into Cedalion and used for the automatic optode detection. First, we are preparing the subject. I'm measuring here the head circumference along LPA, Nasion, RPA, Inion and again LPA, and choose the correct cap size by adjusting downwards. Prepare the cap if not done before and place yellow stickers on each optode. You're of course free to choose any other color, but it's recommended to use a color which is not in the color map of the final 3D image, so it's easier for Cedalion's detection algorithm to automatically detect the optodes later on correctly. Next, I attach the cap, which in this case is an already prepared self-printed Ninja cap here. I mark the fiducials again with colored stickers, which is optional. You can also do it later on by clicking on the 3D image, but it's sometimes easier to detect the fiducials correctly by feeling them. We have here RPA, Nasion, LPA and ZZ on top, then Inion in the back, and I also place here an additional sticker below Inion, which is not really used anymore. It was used in the first version of our algorithm to correctly detect front and back of the head, but as I said, not necessary anymore. Then I check if the cap is aligned correctly, so I have ZZ on top, which should be in the middle of the lines between LPA and RPA, and also Nasion and Inion. And I realign the cap until this is fulfilled. Next point, cable management, very important. We try to avoid having cables in front of our optodes or in the way of our scan. And maybe also check if the optodes are sitting orthogonal to the head surface. Make sure to have equal lightnings for all sides, so I close the window blinds here and place the subject in between the lightnings from the ceiling. Generally, we try to have uniformly illuminated stickers from all directions, so in the end, hopefully approximately the same color code of all stickers. I'm setting up the hardware next. I start the extra recording software, start a new project, choose portrait and hybrid alignment mode. Regarding the resolution, we made good experiences with setting it to 0.5 mm, which is a good balance between resolution and processing time. And then we come to the settings, which we can also change during scanning. We have here the brightness, which we choose depending on the lighting, of course. Working distance, we have here 160 mm to 700 mm, because the scanning distance is around 40 cm. The data quality indicator is switched off here, but used later on to check where we need to scan more. Texture flashing, yes please, and hair mode, no, we have a cap. I start the scan by pressing the button in the middle on our handheld scanner. With this button you can generally change between 3 modes: preview, scanning and pausing, and then it starts from the beginning. And then I start to move the scanner slowly around and above the subject. Slow movements of the scanner are essential because they allow the software to keep track of the already scanned points. The ideal scanning distance is about 40 cm, and the handheld scanner also warns you if you're too close or too far away from the subject. You can see it here. The green bar on top turns red if I'm too close. The same distance bar is also shown on the computer screen on the left hand side in more detail. I continue scanning here. Also note that I started with less difficult regions. So I captured a lot of surface before going to more detailed regions that deserve more time. In difficult regions, like here at the optodes, pan and tilt the scanner carefully to capture everything from all angles. Make sure to have good quality everywhere, but try to be quick. Taking around 3 minutes per scan gave the best results. If the scan lasts too long, the risk of distortion by head movements is increasing. You can always pause the scanning by pressing the button in the middle again, you get into pausing mode and can check where you need to scan more. Also use the data quality indicator to evaluate the quality in different regions. If you want to resume after pausing, press the button in the middle again and you get into preview mode. Keep the scanner still for a few seconds and wait until it recognizes where you are and realigns with the old scan. You see it snapped, and then you can press the button in the middle again, go into scanning mode and continue scanning. In case you lost contact, slowly move a bit back to already scanned regions until it realigns. If that should not be helping, better pause and go to a known region, realign in preview mode and continue scanning. If you're done and happy with your quality, click on optimizing and generating point clouds. Mesh model, and then you can choose parameters for creating the surface mesh. We have here no filter, low smoothing, and only moderate simplification, and we removed spikes, and then click on apply and the mesh is created. Save your scan. Important here is OBJ because it stores not only the point cloud but also the texture information and the mapping. I also choose .stl and .ply just to be complete, and then save the scan of our awesome subject number 1. Very similar to before, I quickly show that the scan can also be done by using a smartphone, and in this case the fNIRS app. After installing, choose Add, Mesh and Small Object and start the scanning procedure as before. I use my iPhone 12 mini here and the free app fNIRS, but you're of course free to choose from any other solution out there, so Kiri, Hedges 3D, Scandy Pro, whatever is on the market for both iOS and Android phones. Regarding resolution, that's a bit difficult to tell. It depends on hard and software solutions. Generally, I recommend not to use smartphones older than 5 years. And in case of iOS, if you have true depth function, this improves scanning resolution. And I, for example, saw some papers out there reporting accuracies of around 2 to 5 millimeters. And the newer iPhones even have LiDAR, so using this, we expect to have a better accuracy also here. But again, we cannot really report any numbers here. So what you see here is I do the same scan as before using the 1-star handheld scanner. Since I can't really assess the data quality of my scan during the scanning process using this solution, I rather do a quick scan and finish everything. Unless it looks distorted, then I would restart. But so far, I just rather do a quick scan and then finish the process. I save the scan and check the resulting mesh. If you're happy, export to OBJ as before, because it not only contains the point clouds but also the texture and the texture mapping, so that we can directly feed it into Cedalion. And then you're done. Let me also quickly show how to post-process the mesh. So in, for example, Mesh Lab, in open source software, I load the OBJ and crop the mesh to everything below the head, which we don't need. In case you need to anonymize your final mesh result due to data protection, for example, feel free to cut out the sensitive face regions. The Cedalion automatic optode detection algorithm will still work. Here in my example, I cut out the whole face, but sometimes you still need Nasion in your final OBJ, so then only crop around it and you're still having an anonymized mesh.